This setup is one of the required practicals that you will need to do. What I have here is a way of measuring the specific heat capacity of this little block. Knowing the specific heat capacity of one of these blocks would enable me to identify what metal this is. Every metal, every substance has its own specific heat capacity, and with this experiment I'm going to measure what that is. So let me talk you through the setup. First of all, I have an immersion heater. Now what I've done is I've just plucked this straight out of the block in the confidence of knowing that this is cold. But you should be very careful because this can get very, very hot indeed. Now this is going to get hot because electricity is going to pass through it from the power pack here, and through ohmic heating, which is something you'll learn about later, this gets really, really hot as a heater would. And it's going to pass its thermal energy into this block. And this block will respond by increasing in temperature. So what you must do is set the apparatus up as shown. This object here is a joule meter. Now this is going to measure the amount of energy that is going through this cable and into this block. There is a more complicated way of doing this, and I'll show you that afterwards. Now another thing that you will need to do is you will need to get a thermometer and you'll place it in the small hole at the side just there. It's always worth just checking to see that it looks at approximately room temperature and that the thermometer is working properly. When it comes to taking a measurement from the thermometer, you should always go down so that your eye is level with the scale. This minimises a kind of error that we call parallax error. More about that another time. So we'll switch it on, and then we will measure at time intervals how much energy has gone in and what the temperature is. So you can see that I have made myself a table in my exercise book, and there is some information that I need to record from the off, and that includes the mass of the block, and I'm going to put a little equal sign there. What I have drawn in this table is the time, and I plan a time interval of perhaps 1 minute, and the energy as read from the joule meter and the temperature as read from the thermometer. Now what is perhaps important here is to draw a circuit diagram, a quick sketch, just to show how your apparatus has been set up, so you can refer to it later. Your immersion heater there, going in, thermometer going in, and it doesn't have to be the best diagram in the world, but the two cables coming down, just so that if in later times you think, I've discovered some amazing law of physics, you can have a little look back and just check that you had set it up the correct way. Then two things coming from here into a power pack. And this is a very crude diagram, but it basically shows how you set this up, and it's a great memory aid for later on as well. Thermometer and an immersion heater, and the block. Of course, other pieces of kit that we have include the object which is always very difficult to draw, the stopwatch, and the laboratory balance, onto which we're going to record the mass. At this stage, it's not worthwhile drawing a circuit diagram, but that's that. Without further ado, let's get on with this. I've been quite excited about this for quite a while. And so I'm going to take the thermometer out. We're going to take the immersion heater, checking to see if it is hot. Take that out. We're going to turn on this laboratory balance. Wait for it to go to 0. And I'm going to place my mass on there. Aha! So it's 1,013 grams. And we want to record that in kilograms. So the conversion would go, you divide it by 1,000. So we put that here, 1.013 kilograms. Now, I'm going to place this back over here, and we're going to put in the immersion heater and the thermometer. And here I have a little bit of oil, and this I'm going to just pour in here just to make sure that the heater is in proper contact with this block. I'll pour in just a tiny drop of oil just to make sure that there's a good connection, and a tiny bit in with the thermometer as well. You don't want to use too much oil, and put it just there. I'm going to switch it on, and it's going to be quite exciting. The first thing I'm going to do though is record where we started. And at time 0, and the energy will be 0, what was the starting temperature? So I get my head as a level, and I think it's 20.5 degrees Celsius. Okay, let's do this. So turn first on this and this. That is off. Turn that on. It is recording 0 joules of energy going in. And I'm going to turn my power pack up because I want it to get hot. I want it to get hot quite quick. So I'm going to turn the power pack right up to 12 volts or 14 volts, whatever it's set on. And I'm going to switch it on and start the stopwatch at the same time. Now, always with a stopwatch, it's worthwhile just giving it a little start and a stop to check you've got a good one. Sometimes you get a dodgy one and you might have to swap it out. So, I'm going to power on the experiment and we're going to start recording. Here we go. So, I've done them both at the same time. Look at that, folks. Look at the energy going in. You can see it going in by the joule. Now, if this gets to 10,000, it'll just start counting again. So you have now the exciting moment of waiting for 1 whole minute. So I'm going to in my time category, in my time column, record 60 seconds, because that is when this gets to 60, I'm going to look at that first. Because that's going quick, I'll take a look at that first and then that second. If there's 2 of you doing this, maybe 1 of you could do that, 1 of you could do that. Alternatively, if there's 3 of you doing it, 1 person could shout out now at the right time, 1 person read that, and 1 person read that. So I'm now 10 seconds away. This is the moment. I can't stuff this up. I'm looking at this, and I'm going to record it as it happens. 3, 2, 1, 1856. 1856, and read the temperature. It is exactly 21 degrees Celsius. Amazing. And I managed to do that in less than 8 seconds. So we'll now wait for another minute to go by, and then we'll have a little read of what it says on the joule meter. Now the temptation here is to start to have a conversation about something totally different. But you've got to keep your mind on the experiment, otherwise it might just, you might miss your chance. There's nothing like the regret of having a really nice set of data in your book and then you accidentally forgot to take a piece of data. It'll be really obvious later. So you've got to concentrate. You can see my little timer here. 1 minute 44, 45, and the energy is increasing. Okay, so I've got to concentrate now. We're in the last 10 seconds before my 120th second. 4, 3, 2, 1. 3698. 3698, and the temperature is now 23 degrees. How very exciting. The temperature is rising because the thermal energy is literally conducting through the metal block. The temperature is rising, and from this we're going to be able to measure the specific heat capacity. Here we go. So, okay, we're going to wait another 40 seconds. A good question is, how much data should you collect? Well, just collect as much as you can. There's no... obviously you don't want to be here for like weeks, but at the same time, the more data you have, the more accurate your experiment is going to be. And so, we are coming up to 180 seconds now in just 15 seconds time. So here we go. Getting into the countdown. 9, 8, 7, 6, 5, 4, 3, 2, 1. 5548. 5548. And the temperature now, oh, it's at 26. Very exciting indeed. And we're going to allow it to go another small amount. It's a good idea to, whilst you're in between times, to think about how many seconds it would be until the next interval. So 240 is my next time, and that is going to be in about 30 seconds time. So here we go. Here is the time creeping up. Now it is possible to do this same experiment without a joule meter, but you would need an ammeter and a voltmeter working together, and we'll probably do that in a different video. So here comes the moment, and it is 3, 2, 1, 7438. 7438, and gosh, yes, we have hit 30 degrees Celsius, people. 30 degrees Celsius. Now, of course, a really important safety part of this experiment is if this goes above about 50 degrees Celsius, it will burn you to touch. And quite often this will be quite warm, and the immersion heater will be even warmer still. And I'm going to take another piece, so 240, so 300 seconds, and I think that is where I will stop, and I will tell you some more things that you just need to be aware of about this experiment itself. So, into the last few minutes. Notice we've placed this on a heat-proof mat. That's to protect the bench, so that the heated thing does not burn a mark onto the bench. And, oh, concentrate, Dr. Boyce, we are near there. 4, 3, 2, 1, 9318. 9318, and the temperature now 34, ladies and gentlemen. Can you believe that? 34. What I'm now going to do is I'm going to switch it off here. Switch it off here, and then I'm going to allow it to cool down. I can stop my stopwatch and allow it to cool down. One of the things that you may notice about the setup here is I've not insulated this against any heat loss. What we may find is that our result might not match the specific heat capacity that we expect. That is because some of that heat is radiating away. If we insulated this, wrapped it up in insulation, then we might get a closer result. So here we have our results. If you've been unable to conduct this experiment, then maybe you could do some of the processing by looking at my results. Take a screenshot now if you want a set of results on which to work. The most important information that we have here, the mass of the block, the energy, and the temperature. So here I have my results. Energy in this column, and temperature in this column. I now want to draw a graph. I'm going to put temperature on the y-axis, and I'm going to put energy on the x-axis. And that was basically because the energy that was being put in was the independent variable. The dependent variable, which normally goes on the y-axis, was the temperature coming out. I'll draw it, and then I'll get back to you. So I now have some axes. In an ideal world, I would like to pick a scale that would have the graph fill most of the graph paper. But you have to pick the best scale that you can. Now I can see that on my y-axis, my temperature needs to go between 20 and 34 degrees Celsius. Now I don't have to start this axis at 0 degrees C. I can, in fact, start it at 20, and that's what I'm going to do. 20, and then 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, and that is where I can stop. I need to make sure that I've included an axis label which describes what is being plotted on this axis. So this is the temperature of the block, And so that I don't have to write the units on every single one of these, if I put a slash and then the unit degrees C, it means that all of these are measured in degrees C. Now, of course, I'm writing this in pen because I need you to be able to see it clearly. If you're drawing a graph, you should always do it in pencil. So 1, you don't smudge it, but 2, that you can use a pencil eraser if you go wrong. Now, on this scale here, we need the energy to go up to 10,000. So I thought we would go up 1,000 at a time. I wonder if I can fit it in. I'll have to write it small. 1,000, 2,000, 3,000. I can see that I'm really struggling, but with a little bit of care is possible. 60,000. Oh no, look, I've gone wrong. Do you see that? I've written 60,000 instead of 6,000. This is exactly why using a pencil would be better, because I could rub that out and start again. I'm going to cross out that 0. So you're just getting carried away. 7,000, 8,000, 9,000, 10,000. It does not matter if you make mistakes, as long as you learn from them. And I also need to put something on this axis here to tell me what this axis is, and this is the total energy provided to the immersion heater, and that is in joules. Now, quite unhelpfully, I've placed my table on the page on the other side of the graph, so I've cheated and I've got my data here. But be aware, if you do that, there is a possibility of a transcription error. You might have copied the number wrong. So the very first recorded point happens to be 20.5, so it's going to be here. And a nice way of doing that is on the y-axis put to 20.5, so I know it's on this line, and it is at 0 joules. So the starting point is 20.5, and I am basically not very close to my graph paper. I need to draw this very accurately. I would get my head really close in there, but then all you would see is the back of my head. No one needs to see that. Let's say the next measurement is 1856. So that's 1, 5, 6, 7, 8 and a half there. Okay, that's the second one. The next one is at 23 degrees, so here, and it's at 3,698. So put that there to remember that. 3, 6, nearly 3, 7. So some people find it very hard to follow a single lineup when they're using both of their eyes open at the same time. You can always close one of your eyes and you'll find it easier to follow the line. The next one is 26, and 26 is at 5548. So 5548 is about there. And then at 30, the next one, 7438. 7438. And then the next one is 34. And that is at 9,318. About there. Now, what is clear is that this is not the best straight line in the world. I think what has actually happened is it took a little bit of time for the temperature to get from the immersion heater to the block. And then it started to then heat at a constant rate. You can see that I can draw a line through these 3 data points here. So I'm going to draw a broken line like this. But I'm not going to continue it down here because I think that this was part of a curve. And so I think that it's so much a part of a curve, I think I might be able to link it. But this is going to be very difficult to do freehand. So I would never do this with a pen normally. But I think the trend, trying to keep my pen on the paper, should look like that. And this is a graph to show specific heat capacity of a metal block. But how does it? Well, you are aware that the equation for specific heat capacity is that a change in energy, an energy going in, which I'm going to represent by delta E, is equal to mc delta theta. That means if you look at this, if I divide both sides by delta theta, delta E divided by delta theta is going to equal mc. Now, a gradient of this graph is going to be equal to delta theta divided by delta E. So that means that the gradient of this graph is going to be equal to 1 divided by the mass times the specific heat capacity. So I now need to work out the gradient of this straight section of my graph. And so I pick a point that might be easy for me to do it from. And it's really hard to guess, really. I think I'll go with this point here because I know exactly where that point is. And I think what I shall do is I'll take it down to maybe there. So take it down to about here. And I'm going to draw this triangle onto the work. Straight down. And draw it across here. Now I know that that point there is at 34 and it goes down to here 26. So I can work out the difference. Here I know that this point, because I've measured it from that point, is at 9318, and I know that this point, the 26th one, is at 5548. Okay, just knocked the camera there. So, as you can see, 34 minus 26 is, not surprisingly, 8. So I know that the rise, or the change in temperature in that triangle, was 8 degrees Celsius, and that the difference in energy was 9318 minus 5548, which is 3,770 joules. So my gradient is equal to the rise, which is 8, divided by the run, which is 3770. So it is equal to a very small number, 2.12 times 10 to the minus 3. Now I've said that this gradient is equal to 1 divided by the mass times the specific heat capacity. So let's take my number and do some things to it. I know that 2.12 times 10 to the minus 3 is equal to 1 divided by, and now I need the mass. And the mass was equal to 1.013 kilograms. 1.013 kilograms times by the specific heat capacity. So I need to rearrange this a little bit. First I've got to get the 1 onto that side. So 1 divided by 2.12 times 10 to the minus 3 is equal to 1.013 times C. So if I do 1 divided by that, and I get an answer of 471.25 is equal to 1.013 times C. The very last thing we then need to do is divide both sides by 1.013, which is going to produce a very similar answer because you're dividing it almost by 1.013, and that is equal to C. So our measurement for C divided by 1.013 is equal to 465.2, and the units are joules per kilogram per degrees C. And that is the perfect way of conducting this experiment.